So 1.7 is linear inequalities and absolute value inequalities. So for day one, our objectives are to use interval notation, to find intersections and unions of intervals, solve linear inequalities, and to recognize inequalities with no solution or all real number solutions. First off, a solvent inequality is the process of finding the set of numbers that make the inequality a true statement. These numbers are called the solutions of the inequality, and we say that they satisfy the inequality. The set of all solutions is called the solution set of the inequality. So remember, an inequality is like our less than, greater than, less than or equal to, greater than or equal to problems. Okay, and so one of the differences between an inequality and an equation is with an equation you'll get x equals a single answer. And when you saw an inequality, you might get like x is less than 3, which means every number that's less than 3 is part of our solution. All right, so one way to write our solutions is in interval notation. So we have what they call the open interval from A to B. Notice it's got parentheses on both sides. Represents the set of real numbers between but not including A and B. So it kind of looks like an ordered pair, but it's not an ordered pair. Okay, it's representing an interval. So it's telling us that all the way from whatever the first number is, all the way up to but not including the second number is going to be our solutions. So like if I have the example right here, the open interval from 5 to 7, that means every number bigger than 5 but every number less than 7 is going to be part of our answer. Then we have what they call the closed interval. It's from A to B, represents the set of real numbers between and including A and B. So notice on the second one here, though, we've got brackets. Brackets represent equal to. If you look, when I draw an equal to sign, it looks like that. And if I connect them, it looks like that square bracket there. Okay? So a bracket has the equal to in it. So it means that those endpoints are included. So if I write using the same numbers here, this means that every number between 5 and 7 is part of our answer. And 5 is part of our answer, and so is the 7. Okay, so the 5 and 7 are included. Now, for the other part here that they show us is where it has a little equation here. And it says, the first one says the open interval from A to B is equal to. This right here is called set builder notation. Okay, it's just another way to write it. Notice both of them, they have something in common. They both are going to have your set bracket. They're both going to have X with a line. And so this is read as the set of all x's such that, and then on the other side over here, we're going to have an inequality. Okay? If it uses a parenthesis, well, first thing is you're going to put your two endpoints for your inequality. So from A to B, skip some space. We're always going to use the letter X between them, because we're just talking about a real number line, so it's like the x-axis. So we're just going to use an X. And then we're always going to use less than symbols. Now, the difference between these two that we're looking at there is if you notice the open interval, the one that had the parentheses on the end, doesn't have an equal to on their inequality. The one that had the brackets on the end, both of their inequalities will have the equal to. So you're just going to have to look at those endpoints and say, okay, is it equal to at the A? If it is, then put your line there. If it's not, then don't. And the same thing for B. Then we have what they call the infinite intervals. And so the infinite intervals are going to have an infinity inside of it. And so remember that infinity is not a particular number. Infinity just means it keeps going because infinity doesn't really exist, okay? But we can keep getting our numbers that are bigger and bigger and bigger or smaller and smaller and smaller depending on if we're positive or negative. So they have the infinite interval from A to infinity represents a set of real numbers that are greater than A. And so we can see they have here our interval notation from A to infinity. Now, since infinity is not an actual number, we can't ever equal it, okay? And remember, the square bracket means equal to, so infinities will always have a parenthesis next to them. So if we do this kind of like what I did on the previous one, if we say it's the set of all x's such that, now, when you go to write this inequality, okay, it's going to go from A to infinity. We're always going to use X, and we're always going to put less than symbols because our interval notation is written smallest number to biggest number. And then look, at the A, it has a parenthesis, so we're not going to put an equal to on that inequality. And at the infinity, it also has a parenthesis, so no equal to at that inequality. Now the difference is here, when we write set builder notation, we don't put infinity inside of it, okay? So we're going to take the infinity and the inequality right next to it off of it. And so we find our inequality then we're going to put in here is A is less than X. Now, that is acceptable, but it's typically not how we see it written. They usually write it X such that, and then X, if it's not like the ones in the previous, if it's just got one inequality symbol in it, they will usually put the X first. So what I want you to do is watch. On here, pick a point. So I'm just going to use the point of my arrow, which is at the A. Just make sure when you flip them around, you flip that inequality and that point is still facing the A. And so that's how they got this as their answer. The next one there says the infinite interval from negative infinity to B represents a set of all real numbers that are less than or equal to B. Notice this time B has a bracket, so therefore that's why it's less than or equal to. So they gave us it in interval notation here. And if I was going to write my inequality, well, for my set builder notation, of course, it's going to have the set of all x's such that. And then we could do the same thing. We could say negative infinity to b, x. We're always going to use less than symbols. The negative infinity has a parenthesis, so it's not equal to. The b has a square bracket, so we are going to put the equal to there. Again, just like in the one above, we're not going to put infinities in our set builder notation. And so there is the same exact thing they had inside. All right, X was already first, so they just left it like that. And then here we've already talked about this, but it says parentheses indicate endpoints that are not included in an interval. So if they're not included, it's a parenthesis. Square brackets indicate endpoints that are included in the interval. So if they're going to be included, if it's equal to, it's going to have that square bracket. Parentheses are always used with the positive or negative infinity because remember we can never equal them. All right, so example 1 says using interval notation. We're going to express the interval in set builder notation and we're going to graph it. All right, so for this first one, for set builder notation, the set of all x's such that we're just going to go from 1 to 3.5, put x in the middle and always use less than symbols. Is it equal to at the 1? Yes, it's got a bracket. Is it equal to at the 3.5? Yes, it's got a bracket. And close your set builder notation. So there is set builder notation. And then it said to graph it. So when we go to graph this, we have our number line. We're going to put our infinities on here. And we're going to put the numbers that are inside our interval. So 1 and 3.5. You can add more to the number line if you want, but you can't have any less. Now, this is telling us in between 1 and 3.5 is our answer, including the 1 and the 3.5. So we're going to shade in between them. Now, before when you graphed in Algebra 2 and below, remember you had open and closed circles? And you had that closed circle, which represented the equal to. Well, when you get into upper level math, they change that, and you're going to use a bracket now. Pretty easy considering we already see what we're going to use in our interval notation. And then remember the open circle was if it was not equal to. And so now we're going to use a parenthesis. And so it doesn't matter which direction it's going to open as far as, you know, I guess it does. If it's on the left, it's going to open towards the right. If it's on the right, it's going to open towards the left. But the main thing is just remember your parenthesis or your bracket is going to open into your shading, okay? So on this one, we can see at the 1, it was a bracket. So I'm going to open a bracket at the 1 into my shading. And at the 3.5, it was also a bracket. So I'm going to open my bracket at the 3.5 going towards my shading. And so there is our graph. So let's try it with the next one. So it says express in set builder notation and graph. So let's do our set builder notation. So it's going to be the set of all x's such that. Now, because this one has an infinity, I'm going to do a little scratch work underneath here and then move my final answer in there. So we know it's going to go from negative infinity to negative 1. We're going to use x's, and we always use less than symbols. At the negative infinity, it's a parenthesis, so no equal to. And at the negative 1, it's got a parenthesis, so we're not going to put an equal to either. We know we're going to take out the infinity and the inequality right next to it. So x is first. So there is my inequality that we're going to write. So we have the set of all x's such that x is less than negative 1. There's our set builder notation. Make sure you close it. And then when we go to graph it, got our number line, we're going to put our infinities, and the only other number we have there is a negative 1. I can see that it's going to start at negative infinity and go to negative 1, so negative infinity, and it keeps going, so I'm going to shade in my arrow, or drawing an arrow there to negative 1, and at the negative 1 it's got a parenthesis, so make sure it opens into the shading. And so there is our graph. All right, to find intersections and unions of two intervals. We're going to graph each interval on the number line, and then if we want to find the intersection, we're going to take the portion of the number line that the two graphs have in common. So remember, intersection is where something crosses, okay? When you think about the intersection of two lines, it's where they cross each other. Think about the x-intercept, it's where the line crosses the x-axis. Y-intercept is where it crosses the y-axis. So to find the intersection of these two intervals, we're going to find where they cross. We're going to find where their graphs will overlap. So for the intersection, I'm looking for the overlap. Now, they usually don't tell me we have the interval from 1 to 3 and write out the word intersects and then like 2 to 6, okay? It's going to have a symbol, and that symbol that we'd be looking for the intersection looks like a lowercase n. The only thing that's missing is that little line, okay? But it looks like a lowercase n for intersection. So that's what we're looking for if we're looking for the intersection. And then to find the union, it says take the portion of the number line representing the total collection of numbers in the two graphs. So when I think of union, I think of like the United States. It's this state, and this state, and this state, and this state, and it's all of it put together, right? So the same thing here. So the union is all of it. So it is everything. So anything that's graphed is going to be part of my answer if I'm looking for the union. So, and just like with the intersection, it's not going to say intersection. Well, union's probably not going to say the union of those two. It's going to have a symbol, and it looks like a U. U for union. The only thing I'm missing again is that little line, okay? It's just like, they're both like horseshoes. But if it resembles an N, it's the intersection. If it resembles a U, it's a union. All right, so example 2. So it says, use the graphs to find the set from 1 to 3, and then that symbol 2 to 6. Well, that symbol looks like an N, so that's the intersection. Remember, the intersection is where we're looking for the overlap. All right, so I'm going to draw my number line. I'm going to put my infinities, and I need all 4 of those numbers in numerical order. So 1 to 3, 2 to 6. You can add the number, all of the numbers in between if you want. You can work on your spacing, but this is the main thing you have to have. So I can, now because I am after the overlap, I'm going to graph above and below, and I'm going to let my number line actually be my answer, okay? So above it here, I'm going to graph the first interval from 1 to 3, including 1 and 3. So from 1 to 3. Below it here, I'm going to graph the second one, which is from 2 to 6. So from 2 to 6, and they both have parentheses. Now, can you see where these overlap? They overlap right here. So it's between the 2 and the 3 is where their overlap is. So my solution, their overlap is between the 2 and the 3. So I'm going to shade that in. And then, what kind of symbol are we going to put at the 2? Well, whatever was in the problem is a symbol that goes there. So the 2 had a parenthesis, and the 3 had a bracket. Or you can see it from above, the parenthesis, the bracket, okay? So there's our graph. Now, it didn't tell me, whoops, sorry about that. It did not say how to state our solution. So in interval notation, you can look at it. We graphed from 2 to 3, so we're going to say from 2 to 3, the 2 had a parenthesis, and the 3 had a bracket. So there's our solution in interval notation. And if we want it in set builder notation, we're going to do x such that It goes from 2 to 3, X in the middle with less than symbols. The 2, is it going to have the equal to? Well, it's got a parenthesis, so no. What about the 3? The 3 has a bracket, so we put an equal to on that inequality right there next to it. And then close your set builder notation. And so there is set builder if it asks for it that way. Now, we don't have another example on here, but I'm going to add one, okay? So this is going to be example 2B. And I'm going to borrow the same number. So we're going to go from 1 to 3 and from 2 to 6. But we're going to now look for the union. And so remember, the union means I'm looking for everything. So on this one, when I go to graph it, I need my infinities. I need my numbers, so -1 to 3, 2 to 6. Make sure they're in numerical order. Now, remember, the union is everything. So, since my answer is going to be everything I graph anyways, I'm just going to go ahead and graph on the number line. You can graph separately and then bring them both onto the number line if you want to. But I'm going to go ahead and just graph it on here. So, from 1 to 3, oops, I'm not sure why I put a negative there. I apologize. So from 1 to 3 with brackets, from 2 to 6 with parentheses. And so you can see where everything is shaded. So we know that all of this is going to be our solution, okay? All of it. Keep the bracket on the left at the 1, keep the parenthesis at the 6. So in set builder notation, we can see that our answer is from 1 to 6. 1 had a bracket, 6 had a parenthesis. Let me go ahead and box my graph. And then set builder notation, the set of all x's such that we're just going to go from 1 to 6, x in the middle with less than symbols. It is equal to at the 1 because of the bracket. It's not equal to at the 6 because of the parenthesis. Close your set builder notation. And there are the different ways we could write our solution. And then to solve linear inequalities in one variable. Okay, so we said the difference at the answer is that, remember, an equation has one answer, and an inequality has a bunch of answers, right? So, and there's only one difference when you solve them. So when you solve a linear inequality, just be careful, because remember, when you multiply or divide by a negative number, you have to flip the sign. So look at this example here. It says 2 minus 3x is less than or equal to 5. Well, we're going to start solving this just like we would any other equation even. So we're going to subtract the 2. And so we get negative 3x. Then you got to check, did my inequality flip? No, we subtracted. So it stayed the same. Then divide by the negative 3. So x, did my inequality flip? Is the number that I divided with on bottom there, is it negative? Yes, therefore it flips. And we get -1. So we know that x is greater than or equal to -1. Now it said to solve and graph, so let's go ahead and graph this. And if you need more numbers on it to help you, you can. But it says x is greater than -1. What kind of numbers are greater than -1? Negative numbers or positive numbers? Positive numbers. So therefore, we're going to shade towards the positive infinity. It didn't have a stopping point, so make sure you draw an arrow. And then at the -1, am I going to use a parenthesis or a bracket? Well, it's got that equal to, so that means that we're going to put a bracket there, opening into the shading. Now, they also didn't tell us how they wanted us to write our solution. It could have just been an inequality, like the x is greater than or equal to -1, or it could have been they wanted it in interval notation. They want it in interval notation. We can see it goes from -1 to infinity. -1 has a bracket, and remember, infinities always have parentheses. Or they could have wanted it in set builder notation, which remember, we're going to use our set bracket, x such that. Now, this has got an infinity, so I'm going to do a little scratch work here. So -1 to infinity, put x in the middle, use your less than symbols. The -1 had a bracket, so put an equal to. The infinity did not, so don't put an equal to. Remember, we don't use the infinity part. So when I flip this over, notice my arrow is pointing at the -1. So X, flip it, -1, and then check. Is your arrow still pointing at the -1? It is. So that would be it in set builder notation. Okay, the only thing here to be careful of is, well, not on this part of the problem, but what if we have a fraction? Remember, though, we've talked about fractions in the past, and so if I have this as a problem, just because it's an equality doesn't mean we're going to do anything different. If I want to get rid of that 2/3, remember I need to multiply by a 3. If I need to get rid of that 3/2, I need to multiply by a 2. So this is kind of like we did before when we did that least common denominator. We said we need to have a 3 and we needed to have a 2, and so that's just what we multiply all of these by. And all of them, remember, all 3 terms, every term gets it. So then your 3 would cancel. So you'd have 2 times, oops, I forgot my x. So 2 times 2x minus your 2 would cancel. So your 3 times 3, your inequality, and then 3 times 2 times 7. And then you would solve that and you'll get the same answer as if you just used your fractions. All right, and then the last one here. So let's solve this inequality. So the first thing we need to do is we need to distribute here on the left. So I got 3x plus 3. I didn't move anything around, so my equality sign's not even going to change. And bring down the other side. Now, here we can differ on what we want to do, okay? Some of y'all are going to say, well, let's move the 3. So I'm going to subtract this 3 over. And so I'd get 3x, my inequality, 3x minus 1. And then I got to get my x's on the same side, so move over the 3x. And this one's a little different because both of the 3x's canceled. So you get 0 is greater than -1. Now some of y'all would have picked a different route to go. So let me work that out. So we have 3x plus 3. My inequality, the 3x plus 2. Some of y'all would have said, well, let's move the 2 first. So we would have moved the 2. You would have got 3x plus 1 is greater than 3x. And then you have to get the x's on the same side. And so you got 1 is greater than, again, that canceled, so it's a 0. The only other option you had, let me rewrite again. Whoops. Is you would have went ahead and moved your 3x to begin with. And your x's would have canceled. Either way you work this, your x's would cancel, okay? So at this point, you have to ask yourself, is this true or is this false? Well, it doesn't matter which way we worked it. Our answer is going to be the same. Is 1 greater than 0? Yes. Is 0 greater than -1? Yes. Is 3 greater than 2? Yes. So they all would have answered true on this, okay? Same problem, same answer. If it's true, your answer is all real numbers. To write that in interval notation, we do -infinity to +infinity. We don't write it in set builder notation. Well, there is a way, but we're not going to talk about it. And so there's -infinity to infinity, and we would shade everything on our graph. Now, what if it had been false? If we'd have done this and it would have been false, so it's a what if false. If it was false, our answer would be no solution. We don't have an interval notation for it, but sometimes you see it with like a 0 with a slash through it. Set builder notation, usually it's just an empty set because there's no answer. And if you go to graph this, well, you have no answer, guys, so there's nothing to shade in.